there, folks. This should be chapter 13. This should be October 14th, but we're on chapter 13. Today we're going to be looking at life. Yeah, I know it's supposed to be an earth science unit, but we're going to look at life because, again, looking at life and looking at fossils tells us a lot about the rocks, and so that's why we use fossils like we do. Again, remember, the only way you can date sedimentary rocks is to understand the organisms that lived there at the time, and so understanding a good geologist understands quite a bit about fossils and how to identify fossils and kind of an idea of where the earth came from. We're going to look at it, it all fits together. So this is kind of a special chapter to look at sort of the evolution of the earth and life together and kind of how they work together. So let's jump right into chapter 13 here. If I can, yeah, there we go. So anyway, your book begins by looking at methods that we study the past. There's a very interesting introduction there about England and a British scientist by the name of Thomas Henry Huxley, who wrote quite a few articles. And he talks about being a teacher and using chalk to write on a chalkboard. I don't know if you remember chalkboards. But anyway, so the chalk itself is actually a rock that's made up of organisms that lived hundreds of millions of years ago. So it was kind of ironic that he's doing that. Now, when we were having class over at the school, the older building, can't remember which building it is now, but the older building has some chalkboards that are actual slate boards. I mean, it's pretty interesting because we looked at them when we were talking about rocks, but their slate boards are actually long, huge pieces of slate, and they just weigh enormous amounts of weigh a great deal. But anyway, so it's interesting. Sometimes we're going to talk about resources here in just a little bit, but it's kind of interesting. Some of the stuff we use every day, we don't realize what it is we're using. So when you're writing with chalk or writing on a chalkboard, you're using some very basic tools of earth science. But anyway, so looking at the past, as you can imagine, it's very difficult unless you know how to read the certain clues. And so that's kind of what this is about learning how to look at these some of these different clues. And here are some of the basic things we would look for, what they're calling ancient origins or ancient mountains. So there's places now where the area is flat, but if you look at the rocks underneath, you realize that, in fact, at one time there was a mountain here, or a big mountain range. And so studying these can give us a good idea of what the earth was like at that particular place at a particular time. Others are growth of continents. And so we're going to talk about continents here in a little bit more in detail, but understanding how these continents formed. Continents over time have formed and then broken apart and then reformed. And so you can sort of see these scars and you can see where things were put together, and then you can kind of work backwards to see where the earth used to be. Depositional environments. So again, looking at sedimentary rocks where you can see if you have a lot of sandstone, then you probably had a river or something that was depositing material there. If you find a lot of limestone, you probably had a shallow sea. If you find mudstone, if you find evidence of volcanoes. So there's all kinds of clues that you can find looking at sediments in these kinds of deposits. Changes in relative sea level, again, looking at the organisms that are left in certain places at certain times can give us some idea of what was going on the planet. So if we have high sea levels, right, then we can guess that the planet was probably warmer. And if we have lower sea levels, we know that a lot of that water was locked up in ice somewhere. So the planet overall was cooler. So by looking at sea levels, that can give us a good idea of what the Earth was like. And then, of course, looking at positions of continents in the past, figuring out now that we know that continents do move around the planet, where they were at any particular time. It's very interesting. So these are just some of the tools that are used. by scientists to kind of look backwards at Earth. So the first uh, eon, really the area of time that we're going to look at is called the Hadean. And so this is the beginning of the Earth. And your book goes all the way back to really the formation of the Earth. So we're back in chapter 2 again, aren't we? Where the solar system comes from essentially a dust cloud left by some large star that exploded. Gravity being what it is, the dust begins to coagulate first into a large star, which becomes our sun. But then some of the leftover material, usually heavier stuff, becomes some of the planets, Earth being one of them, of course. And so the Earth is a pretty violent place where planetesimals and large rocks are smashing into each other and then re-smashing and reforming. And the whole thing, once it's big enough, begins to take on a spherical shape. But there's no really hard surface. Everything is still very hot. Anytime something would start to cool enough, another planetesimal would smash into it, and the whole thing would start over. So for quite a while, the Earth is a pretty difficult place to imagine. Just a big hot rock that's constantly melting and reforming in space. And so this is how the Hadean begins. Your book talks about the fact that just about the time the Earth is kind of starting to cool down a little bit, it's hit by another large object about the size of Mars, and knocks off a good chunk of the crust, and that becomes the moon. Now, one of the theories of this, one of the reasons for this, is when we went to the moon in the '60s and brought back moon rocks. Scientists looked at them and realized they're exactly like Earth rocks. There's not that much difference. So the moon rocks and the Earth rocks are essentially the same. One of the things that was not at the moon, though, is there was no core. In other words, that heavier material in the Earth had already sunk to the middle, and when this object came by, it sort of hit a glancing blow, and it didn't bother that heavy iron, but rather knocked quite a bit of crust off. And so the moon is essentially a big chunk of our crust that got knocked off, and then, of course, over time, congealed again with gravity into what we know today as the moon. So the moon really is a part of the Earth, or at least was a part of the Earth before it was knocked away. Now, as it's cooling, of course, rock begins to form on the surface slowly. Minerals are beginning to form. The atmosphere, of course, is probably nothing we would recognize. Here, your book talks about some of the gases that would have been released into the atmosphere from these rocks that were cooling, like methane, ammonia, hydrogen, nitrogen, carbon dioxide, sulfur dioxide. Pretty nasty stuff. But one of the things you'll notice that's missing is oxygen. There's no oxygen in the atmosphere, and there won't be for quite some time. And we'll see kind of what causes that here in just a little bit. So by about close to a little less than 4.5 billion years ago, the Earth probably cooled enough that liquid water begins to form. And so since we really don't have continents yet, the Earth was probably completely covered in this liquid water to a small degree, or not very deep, in other words. But we have evidence that certain minerals that only grow in water we found at about this time. So we know that the Earth was probably had a lot of water before times that we think of. Also in the next eon here, the Archean eon, is going to see the birth of continents and the beginnings of life. And so this is about 4.4 billion years ago that we begin to see, we talked about oceans, and now we start to see continents appearing. So continents, as we've discussed earlier when we were talking about plate tectonics, continents are different. The continental crust, rather, is different than oceanic crust in that it's lighter and more buoyant. That was kind of one of the weird things we were saying, that rocks can float, and literally rocks float on top of rocks down in the uh, down in the mantle and on these different types of crust. So the continents we're talking about are going to form from lighter materials like granite. Granite, as we know, is an igneous rock that's more of an intrusive rock than an extrusive rock. So the crystals are allowed to form, but it also is a lighter rock than the basaltic stuff we find in the ocean, which is dense and heavy. And so the continents literally began to float on top of the oceanic crust, don't they? And so now the oceans began to leave this level, this material that's floating up, and they become sort of like islands. And the water now is beginning to look more like an ocean. Your book goes into a lot of detail. Please read that, but understand that this is really the basic idea that we're talking about, is that these granites begin to form and begin to be different than and less dense than oceanic crust, and so that what causes them to sort of float above the oceanic basalt. And there, your book has some really good pictures of kind of how this might look, and you can see how then these continents, since they're floating on top of this basalt, can sort of run into each other and crash into each other and kind of form. Here you can see where the whole thing here is separate, but then at some point all gets literally pushed together into one big continent. And then if you know where these pieces are, you can take it apart and understand how this might have formed in the past. So this is how we do it. This is how we look backwards. And the clues are all around us if we know how to read them, and that's kind of the trick, isn't it? Here you see some folks on some very old rock. This is up in Michigan. And so again, remember, this continent, North America, has some of the oldest rock on the planet. And so this is a large, probably pluton this is probably granite. I don't know for sure, can't look at it closely enough. But it probably formed long before North America was even a complete continent and was just pieces of something else. And so it's been pushed up over time and now exposed. And I'm sure the people climbing on it don't even realize how amazing that rock is and how many billions of years old that rock is. This is kind of remarkable at times. But anyway, so this particular eon also is going to see the beginnings of the first life. And as you can imagine, as life begins to evolve on the planet, it's certainly not anything that we would recognize. Life is going to evolve at the cellular level, so the very first organisms are going to be single cell organisms. Cells themselves are probably the first living things, first things that we could define as life. They are microscopic; you wouldn't be able to see them, but we have evidence of those by looking at molecular fossils, by the chemical processes that happen. I don't know. There's a really interesting article just recently about Venus. If you're looking for a good article to do for one of your science inquiry papers, there was some very interesting information found on Venus that leads folks to believe that there may have been life, not necessarily on the surface of Venus, where it's way too hot and way too much pressure, but possibly up in the atmosphere. So you might want to Google that and look. It's very interesting. It was a very interesting article about some folks who were doing some research on Venus. But anyway, looking at what we call isotopic signatures, but again, looking at the changes in carbon, the carbon 12 to carbon 13. Again, this is how we can date fossils, any living organism how it has its carbon is changed from carbon 12 to carbon 13. And then, of course, fossil forms, actually finding images of fossils. So they're going to evolve, but very slowly over time, uh, into from single cell organisms that live, again, microscopically. We can't even see them, and are eventually going to evolve later into multicellular organisms, and we'll see that happen later. But again, this eon here is a very, very long one, and these organisms live for very long periods of time without much change, which is really pretty amazing. They were probably what we call extremophiles. They were probably the very first ones were living in, again, in environments that we just can't imagine life existing in, environments that are very hot, very acidic, very, just you just kind of going, there's just no way anything alive can be there. And yet today, even today, we're finding microscopic organisms living in places that we just literally in volcanoes. And so it's we call these extremophiles. And so now NASA, looking for life, is using some of this information about extremophiles and looking for some of these bacteria that may exist, like I said, in Venus or on Venus, or at least did exist in the past. The next eon is called the Proterozoic eon, and it's the Earth is changing quite a bit. We're going to see quite a few changes. We're going to look at changes in the continents, how the continents now are growing, getting larger, how continents are moving and forming larger groups of continents, and then breaking apart and rearranging themselves over periods of time. We find evidence, again, of these in our own continent. We saw some of the pictures earlier. But in the Proterozoic, which means early life or beginning life, we see the very first multicellular organisms. Now, by multicellular organisms, if you go back to your high school biology, you remember we're talking about organisms not that just live in colonies, not single cell organisms that live in colonies. These are not actual multicellular organisms, but we're talking about organisms that develop different kinds of cells that do different kinds of things, just like you have many different kinds of cells, like blood cells and brain cells and muscle cells and all these different kinds of cells that do different things. And so literally you're made up of a lot of cells, but cells that are specialized, and that's what we mean by multicellular organisms. Your book goes on to, again, look at more complex life. And then here you can see an interesting map about where some of these rocks and outcroppings and where organisms could have been. And again, remember the North American continent. What we see today looked very different back then. It was literally pieces coming together, and here you can kind of see what that may have looked like. But here are the different pieces, right, that are coming together that are going to form. Here is, I think this is Rodinia that they're talking about, where the continents have arranged in this particular fashion. But they're going to change quite a bit over time. So this complex life is going to bring us to the next eon. Your book goes into some of the details of this. Now, this is also a time when organisms are beginning to differentiate in that now we have plants. We have organisms that are absorbing carbon dioxide. They are photosynthesizing. And as you know, the leftover, the waste product of photosynthesis is oxygen. So these organisms are getting much more diverse, and there's many, 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 many more of them. The cyanobacteria and all kinds of different kinds of bacteria that have learned how to get energy, not from, again, the extremophiles were getting energy from chemicals and those sorts of things, but now they're getting energy from the sun and using this process, this new process called photosynthesis. Now, much of the oxygen that they're creating gets absorbed in the ocean. The ocean's a big place, so it absorbs quite a bit of oxygen, so it doesn't affect the atmosphere too much. But eventually, right, the oceans are going to be to their capacity. They can't absorb any more oxygen. Rocks and things on the surface of the planet can't absorb any more oxygen. So the only place it has to go is into the atmosphere. So now the atmosphere is beginning to change, isn't it? That sulfur dioxide is being absorbed and taken out of the atmosphere. Some of that other nasty stuff is also leaving and being replaced by a new gas called oxygen. So literally, all the oxygen in our planet, on our planet today, is generated by, has been over time generated by this cyanobacteria, and then of course now that we have land plants and actual complex plants, it's being generated by them as well. So I used to tell my students always take a deep breath, and every time you exhale, thank a plant, because that's where all of your oxygen came from. And if it wasn't for them, you wouldn't be here. So plants did us a great favor, didn't they? There's an interesting theory that's been around for a while that at some point in this period, uh, the Earth sort of got off tilter a little bit and suddenly became completely enclosed in ice, which is pretty amazing. The glaciers had been coming and going for a little while, but apparently at this point, the glaciers kind of overtook the entire planet, and we call this snowball Earth. We have lots of evidence to show that this was the case, and probably could have stayed the case, except for except for the fact, of course, you remember that the Earth is still hot inside, and so even though the snow and ice was trapping that heat like an insulation blanket, it couldn't contain it for a very long time. But eventually, then that heat and volcanoes and that sort of thing began to reheat the Earth, and the ice disappeared. So we haven't seen that in a while. We have seen glaciers, um, not in the too distant past, but nothing like snowball Earth would have happened. So finally, we're beginning to move into a new phase, the Phanerozoic eon. And again, this is more complex life. This is visible life. So these are multicellular organisms. And this is going to happen at a time um, when the Earth is, again, getting a lot of oxygen. So now organisms are developing not just as plants, but now as animals. So the plants came first, generated the oxygen. Now life has transitioned into living organisms that can take this oxygen, right, and metabolize it, and then they release carbon dioxide. So this is that interesting, dichotomy we have of living things, plants versus animals. Plants taking in carbon dioxide, releasing oxygen. Excuse me. Animals taking in oxygen and releasing carbon dioxide. And here's a really interesting chart that shows you these oxygen levels as they begin to rise. Here, about 2.5 billion years ago, they begin to rise, and all of a sudden they jump through the roof. Now, this is the time of the about 500,000. This is what we're going to look at here in just a minute. The Cambrian explosion. This is all Precambrian here, and then this is all Cambrian. And then eventually we're going to see this big rise again with the dinosaurs. And so these are oxygen levels as they were at the time. This is the big die-off, the great extinction event that happens where we lose a lot of the plants. So oxygen is not being made, but organisms continue to grow, and the plants continue to grow as carbon dioxide levels rise in the atmosphere, and that oxygen goes back up. So it's all a cycle. It's all one thing balancing another. If you get too much oxygen, then animals get big and plants die back. But as plants die back, animals don't have enough food, so animals die back. When animals die back, carbon dioxide levels go up, more plants begin to grow, and so the whole thing is just a big teeter-totter that can go back and forth over time, which is just absolutely fascinating when you look at all this evidence. So here we have the Paleozoic era. Continents are coming back together. We're starting to see, again, larger continents. We're beginning to see these shallow seas, which are going to make up. This is where our state, Kentucky. There you can see Kentucky right there in this particular picture here of what's going to become North America. But here you can see Kentucky, and again, it's part of this shallow ocean. Again, the water was probably no more than 40, 50 feet deep. Lots of light came through, so you had lots of coral, lots of other kinds of ammonites and all kinds of critters that you can go see even today down at the Falls of the Ohio. You can see these guys and in some of the fossils that you can find in almost any stream, any river, any creek around Kentucky. If you start walking around in the rocks, you'll see these leftover plants and leftover animals. It's just pretty amazing. So life is going to kind of explode at this period. 541 million years ago, we call it the Cambrian explosion because we find a lot of these fossils, and they again are just creatures that you just can't imagine how crazy they look. And again, they're all still in the ocean, aren't they? There are no land creatures yet. Everything still lives in the ocean. Why is that? Well, because if you climbed out of the ocean, right, the radiation from the sun would kill you eventually. This goes for plants or animals. So if you lived back at this time, just 500 million years ago, you'd have to live in the ocean because the ocean acted like a shield. Now, what's going to happen, of course, as we now know, because we're living on land, right, and we can get a little radiation if we get sunburned, but nothing like it would have happened to you back then. But now, of course, there's enough oxygen that, in fact, the oxygen has created something called ozone. And ozone is, if oxygen that you're breathing right now is 2 molecules of oxygen, ozone is 3. And so that larger molecule acts as a filter. It filters out most of the harmful ultraviolet radiation from the sun, and allows us to live now on the planet. But at this time, everything lived in the ocean. So most of the fossils, as a matter of fact, all the fossils, again, that you might find around here are going to be organisms that lived in the ocean. Of course, it's a narrow range, isn't it? Because you live in the ocean, but you need sunlight. So you can't live in the deep ocean unless you're an extremophile. So you've got to live in these shallow oceans. And again, it's why we just have fossils coming out of our ears here in Kentucky and Indiana and Tennessee and places like that in this area. So again, life begins to evolve. We're looking at the different time periods of the Paleozoic, the early, middle, and late. The Carboniferous period is one of the later periods, and again, this is where all the coal comes from, right? Carboniferous means coal, and these were probably giant forests of plants that are eventually going to spring up on land. And once organisms can crawl up on land, they do so in abundance, and the whole evolutionary process begins on a whole nother scale, doesn't it? So then, yeah, these animals become adapted to land, and are able to walk about and find food. And that's really the whole point of it, isn't it? Is that the idea of natural selection, the idea of evolution is adapting to environment. So as the environment changed, as there became oxygen in levels that were not only breathable, but also ozone levels that were protecting us from the sun, animals and plants took over the dry land. Excuse me. So your book goes into a little bit more detail on what's happening at this period. And again, you can see where this material is. Let's see. not necessarily. I was thinking of something else here, but anyway, um, if you do get a chance to go over to the Falls of the Ohio, go through the museum, and it's really neat. You'll see these rock columns, and you'll be able to see where in time these organisms that you'll be looking at when you go out on the rocks, you'll see where they come from. Um, but anyway, again, there's lots of detail here. Uh, and then we jump into the Mesozoic era. And again, these are our dinosaurs, right? Uh, we're in the Jurassic, the Triassic period, and then finally the Cretaceous period. And these are the dinosaurs. Dinosaurs are pretty fascinating. Of course, kids love dinosaurs because they're really cool. Um, and they are really cool. But they live at a time where carbon dioxide levels are very high. So there's lots of living things, there's lots of plants, there's lots of food for them to eat, which is basically why they get so big. We think of dinosaurs, and the word actually means terrible reptile, terrible lizard. But in fact, they probably weren't reptiles, are they? They weren't warm blooded, they weren't cold blooded. They were kind of, excuse me, kind of a medium blooded. Um, not warm blooded like us, but not cold blooded like a snake or reptiles today, because they did move around quite a bit. And we find their fossils in lots of different places. And of course, the Earth was a much warmer place at that time as well. But these are the organisms that are going to be kind of taken over at this time. And they are not, again, not reptiles. And our evidence now shows us that they probably weren't even have reptile skin, but probably had feathers. We're now seeing dinosaur getting fossils and learning that dinosaurs probably had more feathery skin rather than um, skin like a lizard or a snake that we think of today. And then, of course, eventually we have discovered the dinosaurs. A lot of the dinosaurs did not die in that fiery meteor, but probably evolved into birds. And it's just kind of funny because I raise chickens and I love fresh eggs from chickens, so I've got some chickens here with me. And it's every time I look at a chicken, all I can see is dinosaur. And if you've ever looked at one closely, you can see dinosaur. You can see it in their eyes. You can see it in the way they move, and you can see it in their feet. Their feet are just dinosaur feet. I mean, it's really amazing to look at a chicken. And every time now I can look at a chicken and just see a dinosaur, which is just kind of crazy. But anyway, this is again interesting because we find all these fossils and we know so much about the different types of dinosaurs there were. I guess that's why it's such an interesting thing. But life will move on, won't it? And eventually the dinosaurs will pass away. Um, and again, it was probably a combination of volcanoes and a meteor that hits the Earth about 65 million years ago that's going to cause the demise of the dinosaurs. And it's a good thing, especially if you're a mammal like us, because once the dinosaurs now are gone, um, now the mammals have a chance to evolve. And again, if this meteor had not hit the Earth, then we would probably not be here. It's a good guess. So it's a very interesting story here. Read this about the KT boundary. Very interesting story about the Alvarez father and son team who discovered this. And again, when they came up with this theory back in the 60s, people just thought they were crazy. Very similar to Wegener, when he was talking about continents moving. The fact that a meteor would cause the dinosaurs to disappear was just crazy. But as the evidence began to pile up, scientists began to agree. The problem, of course, was finding the hole. If a meteor hits that big, where's the hole? And that was discovered, I think, back in the 80s. I think that's what your book says, that they finally discovered here in the Yucatan Peninsula, what's called the Chicxulub crater. They found the hole where that particular asteroid hit. Of course, it was all covered up. That was the problem. Of course, 65 million years of of um, things moving around would cause it to get covered up, and so we didn't actually see it, but you could see it under the ground. And so there's quite a bit of evidence now that that's exactly where things hit. Finally, the modern world, the Cenozoic era. So we live in the Cenozoic era, and again, thanks to the dinosaurs being sort of put in their place, as it were, other organisms like mammals began to evolve, and the world began to change and mutate into what we see today. The continents move into relatively positions that we think of today when we look at a world map, right? But again, remember, we're just looking at a snapshot in time. Continents are still moving. If you took this class, say, 20,000 years from now, right, the world map would look a little different. We're just, again, this is like slow motion. The continents are still moving about 2.5 centimeters every year. Things are going to change. Things will change, and things will be very different eventually. But because they are changing positions. We do have the ice ages, which again is a whole other very interesting thing to look at. We'll look at that in some detail in just a little bit. But the fact that we get these ice ages off and on, organisms can move and can reposition themselves. It's interesting when you look at this to imagine that a species like the marsupials actually began in North America. So marsupials, we're talking about kangaroos, right? Kangaroos actually, were evolved in North America, but there are no kangaroos in North America anymore because they moved to a different area, and then that area moved away, so they sort of got stuck on the island of what became the island of Australia. Interesting, the only marsupials that are still living in the United States are possums. And so possums, those nasty little critters that come out of the woods at night, are the only marsupials left in the United States. So we see a lot of that where organisms are moving around, and because things shift, the ocean sea levels will drop when we have a glacial event. When they drop, then you get land bridges. Organisms can move from one place to another. But then when the glaciers begin to melt and the oceans reform, those land bridges disappear, and now what used to be a peninsula becomes an island. And so organisms can get, and we're talking about plants as well as living animals, can get stuck. And so we see that all over the planet, which is very interesting. So anyway, this is a very good little picture here that kind of shows some of this history. So put that, make sure you look at that carefully so you can understand. It kind of goes through the whole timeline here, which is very good. And then, of course, the last thing we want to talk about is kind of where we are today. There's some folks that are beginning to talk about a different period in time and we call this Anthropocene period. Anthro means human, and so we noticed that these time periods, right? All those little time periods, they happen because something changes, something big changes. Either organisms begin to evolve, or there's a big extinction event, organisms disappear, but something happens, and that's what causes these new time periods to come up. And so the argument is there should be a new time period because something has changed. Human beings are here and are capable of changing the environment, aren't we? I mean, think about it. We're able to change the weather. We're able to change the land. We're able to change, everything. And so that's never happened before. We're the first organisms that literally are capable with, if you want to just say nuclear weapons, we're capable, aren't we, of wiping out all life on the planet if we wanted to. If things had really gone bad back in the 60s, when everyone was collecting nuclear weapons and aiming them at each other and threatening each other, if things had gone bad, it's quite possible that there wouldn't be a 70s or an 80s or a 90s, that we could have wiped out all the life on the planet. So we've probably entered a new period called the Anthropocene period. And it's going to be interesting to see how that ends up. I'm hoping that we'll be a little bit smarter than we appear to be now, and don't dismiss science as much as we are, and hopefully take global warming seriously. So, and again, we'll talk about that later in the last chapter. But here's your review questions. If you're going to use them, that would be great. And I will see you in the next chapter.